Hello everyone. Welcome to the series of design and analysis of algorithms. So in this session, we will be learning about one more important concept, which is the heart of the design and analysis of algorithms. So throughout your syllabus, you should be aware of this space complexity and the time complexity. All for each and every algorithm, we will be calculating this. Okay, so let us get into the details. First, let us see what is meant by space complexity. Let us see the definition of it. So it is nothing but the amount of computer memory it takes to run to completion. How much memory is required by the algorithm or a program in order to run. So that is called as the space complexity. So which can be expressed as S of P, space complexity of problem. It is not program, it is problem because we are dealing with algorithms, not with a program. I hope all of you are clear with what is an algorithm and what is a program. Okay. A program is specific to any particular programming language. Whenever we talk about algorithm, irrespective of the programming language that you are working with, we will be writing the steps of the algorithm. So only here we are mentioning this as a problem, not as a program. Okay. So the space complexity of any problem, S of P is equals to C plus SP of I. Here C is called as the fixed part. Okay. So it is independent of the instance characteristics of the program, like what is the number that you are working with, or what is the size of the input and output that you are giving. So what comes under this fixed part is the instruction space. So the space needed in order to hold all these instructions, and space for some simple variables like, can you tell me some simple variables like int A, int B, X and Y? So all those are the simple variables. And fixed size component variables. Okay. So for example, if I have an int array of size 10. So here how much space do I need? I need space for 10 integer variables. Okay. So let us don't talk as in terms of bytes, but let us talk it in terms of units. Okay. So we are talking about this in terms of units. The reason is we are not talking to related to a particular programming language or to a particular programming interface. So I'm not talking in terms of bytes, but we are talking in terms of units. So depending upon the programming language you are working with and the system that you're working with, that means is it 32-bit machine or a 62-bit machine, based on that the number of bits will vary. So only I'm not talking in terms of bytes, but we are talking in terms of units. And space for constants. For example, if I have a is equals to 5, so this is my constant. Okay, so like this, I need the space needed for all these constant variables. So here the space requirements are not going to vary. Okay, so all these sort of variables we will be considering under the fixed part. Next, coming to the variable part. So this variable part is dependent on the problem instance characteristics. Okay, for example, the space needed by reference variable and the recursion stack. So let us take the same example of int a of n. Okay, so here I didn't specify the size of n. Somewhere I might have defined, or I will be reading this from the keyboard. So depending upon the size of the variable n, my memory requirements might change. And also when we are working with recursion programs, so there depending upon the n value, the depth of the recursion will change. So there my requirement is different. So here, before running the program, I doesn't know my memory requirement. So I'm calling this as a variable part. Okay, are you clear with what is fixed part and variable part? So in the fixed part, I clearly know what is the amount of space needed for my program in order to run. at the time of compiling itself. Before running itself, I know. So whereas in the variable part, I doesn't know the memory required by the program until I run the program. Okay. So when you will supply this n value, so when you are running a program, so there you are supplying from the keyboard, right? So unless I supply this value, I doesn't know what is the memory required by this program. So this part I'm calling as a variable part. So we will see examples for all these cases, then you will be even more clear. So first let us see one simple example. Okay. So here you can see algorithm ABC, which is accepting three simple variables A comma B comma C. So here we are not talking about the data type also. Okay. So we have three simple variables. What it is doing? So it is performing some calculation and then it is returning the value. Okay. So let us calculate the fixed part and the variable part separately. And then let us add up as S of P. So first let us calculate the fixed part. Okay. So here how many variables do I have? I have three variables and whatever intermediate calculation is done. Okay. So this is not, you are not storing the result of this in any variable. So I doesn't need any memory for this particular calculation. Okay. So only I need space to store values of A, B and C. So that means I need in my constant part, I need only 3 units of space, each for variable A. For a variable A, I need 1 unit. For variable B, I need 1 unit. For variable C, I need 1 unit. So now, after computing this, here I am returning the value whatever is computed. So that means you are returning to a particular location. So all the time when you I think all of you are aware of the return address. So whenever you are compiling a program, so this return address will be saved in a stack. So from there you have to retrieve the return address and then send this address there. So for this return address, definitely I need one space. Okay. So along with these 3 units, I need one more unit of space for the return address. Okay. So altogether, how many units am I requiring? I need only 4 units of space. So all this is my constant part. Do I have any variable part here? Okay. So is there any part which is going to change with the input that I am supplying? No, nothing. The memory requirements are not going to change. So I can say SP of I as 0. Okay. So now what is my space complexity? S of P is C plus SP of I, right? So this is the formula that we have seen in the beginning, SP of I. So it is sum of fixed part and the variable part. So here my fixed part is only 4 units, whereas my SP of I is 0. So altogether my space complexity is 4 units. So now let us talk in terms of a specific machine. Suppose if I am working with a 32-bit machine and let us assume that the type of the variables is integer. So then how many bytes of memory does it require? Okay. Integer means in a 32-bit machine, the size of int is only 2 bytes. So 2 fours are 8. So totally I need 8 bytes of memory. That's all right. 8 bytes of memory. Suppose if I work with 64-bit machine, then the size of the integer is 4 bytes. Okay, 4 fours altogether 16 bytes of memory I need. But this I know at the time of compilation itself, right? So I'm safe. That means my system is safe. I'm not going to be into trouble. Okay. So this is how you can convert the number of units into number of bytes when you know what is the programming language are you working with and what is the machine that you are working with. Okay. So basically, we are talking about the memory requirement of the program. Let us see one more example. So here you can see this is a iterative program. Why I'm calling it as an iterative program? Because here I have a for loop, and this loop is going to run for n number of times or n iterations. So this is a iterative sort of program. So now if you see what are the inputs that I am having, A, which is the name of the array, and n, the size of the array. So two variables here I am having. Okay. So that means how much memory do I need for the array? So a total of n units I need. So let us imagine n value as 5. So that means I need an array of size 5 units, right? I think my video is going bit lengthy, but I want all of you to be clear with this basic concept because this is heart of design and analysis of algorithms. So this is the heart of the whole subject. Okay. So a total of 5 minutes of space is reserved for this array. Okay. So now, do we have any simple variables? Yes, we do have. So we have a variable s which is needed for storing the result. And similarly, I have a simple variable n which requires one more unit of space. And here I have a return address which needs one more unit of space. Okay. So suppose if we think that we doesn't know the n value. Okay, so let us take it in general. So then how many units do I need? I need n units. So this n, how should I consider it as? Shall I take it as C or shall I take it as SP of I? Yes, I should take it as SP of I. So because depending upon the n value, so this memory requirement is going to change. Say suppose I am accepting this value from the input device. So then my n value I will be giving differently from time to time. So depending upon my n value, the memory requirement is going to be changed. So I'm taking this SP of I. Okay. So next, let us take the constant part. What is the constant part that I have? The space needed by simple variables. Here I have three such values. So C value is 3. So what is the total space requirement of this problem? It is n plus 3 units. Okay. So if you want to convert this into number of bytes, suppose if you are working with 32-bit machine, let us take n as an integer only. And here if you see, this is a floating point variable because s value is given as 0.0. So it is a real number. So how many bytes are required? So it takes 4 bytes of memory for S and 2 bytes for I. And the value that it is going to return also will be a real number. So another 4 bytes. And then 4 plus 4, 8. 8 plus 2, 10. Okay. So 10, not 10 units, 10 bytes. So 10 bytes of memory I need. So if my n value is 1, suppose if my n value is something else. So based on that, again, my requirement is going to change. So that you can just compute and check yourself. Okay, so like this, you can calculate the space complexity. So let us see one more variation. So now we are coming across with recursion. Okay, so here if you see the algorithm recursive sum of a comma n. How can I say it as recursion? Here you can see the algorithm name rsum. So this is called inside the algorithm. So whenever I'm calling the algorithm inside the body of the algorithm, this I call as a recursive algorithm, right? This is the basic definition that we know already. Okay. So now, so this part is, this algorithm is containing two parts. Okay. So here, if n is less than or equals to 0, then return 0, 0 0.0. So this is the base condition. And this is the recursive part. So now, in this case, we have to evaluate the memory requirement separately for both the base condition as well as for the recursive part. So if you take the base condition, so here what are the variables that you have here? So you have a simple variable n and then you have a return address, right? So that means for n we need one space and for the return address one more space. And then here I have the recursion equation. Let us assume some n value and let us expand this recursive equation. Let me take the n value as 3 and let me expand this equation. So now here we have the expansion for the recursive equation. So this is the recursive part, right? So when you take n value as 3 and substitute in this, okay, so a comma n value is 3, 3 minus 1 is 2, r sum of a comma 2 plus a of 3. Similarly, n value is 2 now. So r sum of a comma 1 plus a of 2, r sum of a comma 0 plus a of 1 when n value is 1, when n is equals to 0. So this is the equation. So now we reach to our base condition. Whenever your n value is less than or equals to, so here we reach to n equals to 0. So then ultimately what it will do, so it will return you a value of 0. So that return value will be substituted in this equation and this will be computed. Then again that value will be substituted here, added up with a of 2. Then the result is again passed on to r sum of a comma 2 and it is added up with a of 3. So this is how your recursion is going to work. So here, what is the depth of the recursion? For any recursive equation or for any recursive algorithm, the depth of the recursion is n plus 1. So here you can see n value we have taken as 3. But totally how many recursive steps you have got? So you got 3 plus 1, a total of 4. So now how many variables do we need? In each recursion, how many variables are we taking each time? So here, if you see, you need one unit for n value and you need one value for the return address, right? So every time whatever value you have computed, that you are returning back to the calling function. So for the return address you need one more and you have to refer to the array location, right? So one more space you need for a. Okay, so a total of 3 units of space you need in each and every recursion. So like that, how many steps do you have? A total of n plus 1 you have. So what is the space requirement? So it is 3 into n plus 1. So here the constant space that you see, it is 3. But here we are not adding up, but we are multiplying it with this. The reason is the depth of the recursion is n plus 1. Okay. So this is how you have to work with any recursive algorithm. So this is the S of P. So here all the time we will not give equality, but we will give greater than or equal to. Okay, so the reason is there can be some minute additions in the variable requirement and the here actually we are not considering the space for storing this program. So temporarily also all the computed values will be stored in a temporary space and also that we are not taking here specifically. So only this inequality greater than or equal to. So hope you followed this video. If you have any queries, do let me know in the comment section. Thank you.